Hello, Professor.
Hello. And so I've started the recording and we can get started here. Hopefully everybody can see my screen.
Yes, we can.
Perfect. So if I forget to do this, somebody please remind me. What I want to do is at the start of each lecture, I would like to just start by asking if anybody had any questions from the previous lecture or anything that they've read or anything like that. So I just want to start it off by asking if anybody has any questions for me.
Professor, I took a look over the homework. I just wanted to check that we haven't went over the material for the homework, right?
Yes, that's correct.
Okay.
But it's not due for a week.
Right.
So yeah, I just wanted to kind of get it in your hands. I didn't want to spring it on you at the last second. But yes, hopefully tonight and Thursday night will cover everything you need for doing that homework.
Another question: the code, should we have it in a hard book form, or could we have it as a PDF online?
I think for the code, you could go either way.
Okay.
I don't think the code is going to be absolutely a necessity for taking the test or tests.
Okay.
But just remember that anything that you have in a digital format, you're not going to be able to access it during any of the exams. But the code is really more for reference, and it's really more for long term. So that it's so much easier if you get into the habit of looking up where things are as you're learning them, then it's so much easier that way than trying to relearn it after you learned how to do concrete design and then go back and try to find where everything is in the code is a lot harder. But it wouldn't bother me if you had it in the digital format. I think you'll be okay with that.
Okay, because for the book, I ordered it on Saturday, and then it wouldn't arrive up until next week. It's taking a week to so I could get it.
That's a bummer. Okay.
Yeah.
Okay. Hopefully you get it as quickly as you can. I think the lectures, I think you're going to be okay. You can get caught up pretty quickly. This lecture and the next lecture are pretty theoretical, and I think you'll be okay.
Thank you, Professor.
Anybody else have any other questions? Okay, then let's get to it for tonight. Tonight we're going to start with flexural analysis of beams. That's kind of the common starting point that most concrete design courses will start with. And we will get started. Okay, so let's start by just thinking of a simple span concrete beam in flexure. So just a concrete beam spanning from support to support with some kind of a uniform load on it. And as we apply load to this beam, it's going to crack because concrete cracks. That's what it does. Concrete is not very good in tension, but it's pretty good in compression. So as you apply the load, you'll see a cracking pattern like so. With increased loading, you might see a cracking pattern like that. We expect to see 3 stages of flexural behavior. So going from no load to a little bit of load to more load to more, as we increase the load, we're going to go through 3 stages of flexural behavior. And I put this over here for reference. This is from last lecture where we had the stress strain for concrete. And I superimposed the stress strain idealized for rebar. So the rebar goes up to, this is 60 grade rebar, it goes up to 60, and then it's just assumed to stay at 60 for all of eternity. Sorry about that, somebody's car alarm going off in the background. Okay, so stage 1 is uncracked. The uncracked stage for a concrete beam, the concrete is basically acting like an elastic property, both in tension and compression, and it will act as like a, what's the word I'm looking for? Anyway, an elastic material in both compression and tension to a point. And so you can kind of make the point that if this was like a 5-foot deep concrete beam spanning 20 feet, you could expect, even with no reinforcement at all, you could jump up and down on this beam and you're not going to crack it. It does have some strength before it gets to the crack stage. Second stage is cracked and elastic. So you do have the tension side of it has cracked, but on the compression side, you're still kind of in this flat area over here where the material is acting elastically. And then finally, you'll have an ultimate strength level of behavior where the steel has started to yield and the concrete is in this plastic range. That's the ultimate strength level. Okay, so looking at this kind of from a side view, here's a beam, concrete beam, that has steel reinforcement in it. And what I'm looking at is this is a strain diagram. This is a stress diagram. So the strain in concrete beams is always assumed to be linear. That might vary, this might vary, but it's always a straight line linear relationship for strain. Stress at the beginning is a straight line linear assumption before it cracks. So at low stresses, it behaves kind of like a linear elastic material, but the strain is always linear. Okay, any questions so far? Okay.
Could you just the stress, so it's here it's shown as a linear, right?
Okay, so at low stress levels, at low strain levels, the rebar is linear,
right,
and the concrete is linear in this very small region down here. And it's very hard to see, but there's actually a little bit of it going into the tension side as well. So at low strains, both the steel and the concrete are acting linearly and elastically. So your strain is linear and your stress is linear as well. The red line represents the stress in the steel.
Okay.
Okay. So if I go to the next stage, the next stage, you see that the strains are larger. It's still linear, and the strain at every portion of this concrete beam and steel is proportional. So this, you can draw similar triangles to find what the strain is at any given point on this beam. But the strain is still linear. However, the stresses, you no longer see concrete stress and tension. The tension side of the concrete stress is gone because the concrete is now assumed to be cracked. Cracked concrete doesn't carry any tensile force. And then the stress in the steel is still represented by the red line. Okay, so now we've just progressed a little bit farther. We're beyond the concrete's ability to carry tension, but we're still in this range over here on the compression side. So the concrete's still acting linearly in compression. So the next step is the ultimate strength level. The strains are much larger now. I've changed my designation from epsilon concrete and compression to epsilon U ultimate strain in concrete. The strain in the steel is much larger now, as you can see. And the stress, this is the importance of this part of this, is that the stress now is not linear. So this strain is about over here at this strain, way over here. And so the stresses out in this range here are plastic. And so the stress in the concrete is this plastic shape. Okay, any questions about that?
For the strain, at the ultimate strength level.
Here, uh-huh.
Yeah. What's the reason for why the epsilon s is? Oh no, I get it now. I understand it now.
Okay, answered your own question?
Yeah, sorry.
No problem at all. So the strain in the steel is increasing at every step, but the stress in the steel is basically following this red curve here. You're either in the elastic range or in the plastic range. And the stress in the concrete is following this curve. So as the strain goes from small to medium to large, you can follow the stresses with this curve. And that's what this is representing. Okay, so the reason I bring this all up front is when it comes to designing concrete beams, we're going to design certain aspects of it in the uncracked region. Some things we're going to design in the cracked elastic region, namely these two regions here will be deflections and or cracking analysis. And other aspects of concrete design is 100% in this ultimate strength level, where what we're trying to do is capture what is the absolute maximum load that the beam can carry, and then we're going to compare that to some factored load to be sure that we're still in the safe region. But since concrete is fundamentally a nonlinear material, it makes more sense to design our ultimate capacity using this philosophy, this ultimate strength level. Okay, now we're going to define this, the ratio of the stress in the steel to the ratio of the stress in the concrete is what's known as a modular ratio. And what that means, or the modular ratio, is designated as a little n, and it's as defined as the Young's modulus of the steel divided by the Young's modulus E of the concrete. And what this is really trying to say is that at any given strain, in fact, let me try to do my little tool here. Okay, so if I were to look at the strain at this point right here, you can see that the stress at that strain in the concrete is much lower than the stress in the steel, because the steel is so much stiffer than concrete is. So the modular ratio is really how many more times higher is the stress in the steel than the stress in the concrete at the same given strain. That's what that definition is. Okay, any questions on that? Okay, so now we're going to talk about cracking moment, because the cracking moment is the applied moment that separates us from an uncracked beam to a cracked beam. So it's the flexural moment that causes the first cracking in a beam. Moving from stage 1 to stage 2 can be found. This moment is known as the cracking moment. A beam will crack when the applied moment causes stresses that exceed the modulus of rupture. If you remember from mechanics of materials, stress is equal to minus my over I, where moment of inertia, the applied moment, and y is the distance from the neutral axis to whichever point on the beam you're looking for the stress. In concrete design, we replace sigma with F sub C. F prime C is a design strength. F sub C is just induced stress in the concrete, right? So if I can have a design strength of 6,000 PSI, theoretically, that's the stress at which the concrete will fail. But I could have F sub C of any stress up to 6,000 PSI. That's just the stress that's induced in the concrete due to the applied moments. So F sub C is minus my over I. If we replace f sub c with f sub r, the modulus of rupture, and solve for the cracking moment, we get, so I just rearrange this, and I can get m cracking is equal to minus times the modulus of rupture, f sub r, times I over y. Finally, if we mistyped there, if we, the gross moment of inertia, and take y as the distance from the center of gravity to the tensile face, y sub t, then we have m cracked is equal to the modulus of rupture, I gross over y sub t, where the modulus of rupture, we talked about this last time, is minus 7.5 lambda square root f prime c. Okay, any questions before we get to our first example?
Professor, I noticed that on the book, the M cracking is given in a positive, whereas here you're giving it in a negative. Is there like any differences in the sign convention in that case, or?
Good question. What I've done is the sign convention should be that concrete in compression is positive, concrete in tension is negative, and F prime C is always positive. So the only way to get the modulus of rupture, which is a tensile stress, to be negative is you have to have a negative on here. So F sub R is negative, and M cracked is the negative of a negative. So M cracked is going to be a positive moment. I'm not quite sure how the book justified that. They very well might have just left the negative off of here and here, which gives you the same result.
Right.
But I was trying to be a little bit more technically correct. Yes.
Consistent.
Consistent.
All right.
Thank you. Yes. So this is the equation for mechanics. And if you plug in a negative for concrete in tension, then you get the same answer. Yes.
Thank you.
Yes, good question. Okay, so we're going to do our first example. Here's a concrete beam with steel reinforcement. The steel reinforcement is 2.5 inches from the bottom of the beam. The width is 18. Overall depth is 30 inches. Find the stress at the bottom of the beam and at the steel for a 30 kip-foot moment. Find the cracking moment for the following beam section. And I assume that concrete is 6,000 psi. So my solution, part A, I need to know what y sub b is to the center of gravity. So center of gravity of a rectangle is just halfway up. So I take h over 2, 30 over 2, it's 15 inches. I have to find my gross moment of inertia. Hopefully everybody remembers from mechanics that it's bh cubed over 12. So 18 times 30 to the third over 12 is 18,000 inches to the fourth. I'm going to have some typos now and then. I hopefully will just catch them before I put them up on the screen, but not always. That should be inches to the fourth. Okay, so the stress at the bottom of the beam, F sub C is MYT over IG. There's a negative in there. So I have minus 30 kip feet. And then I put this, you're going to see this a lot in this class. I'm trying to be technically correct and consistent wherever possible. This is 30 kip feet. This is inches. This is inches to the fourth. So I need to convert my moment to kip inches. So I'm going to put this little conversion factor in here that you'll see a lot, 12 inches per foot times 15 inches over 18,000, again, 8 inches to the fourth. And that's going to equal minus 0.3 KSI or minus 300 PSI. And this is at the bottom of the beam, so it's in tension. Now I can look at the stress at the steel. In order to do so, I need to find my modular ratio. So the modulus of elasticity for concrete, 57,000 square root of F prime C, 57,000 square root 6,000 is 44 4,415.2 KSI. Modulus of steel is always taken to be 29,000 in this class. So this, you don't even need to calculate this or anything. Just the modulus of steel rebar, always 29,000. The modular ratio is 29,000 over 4,415, which is 6.57. The KSI is canceled. So the stress in the steel is my over I times N, because it's very important you get that N in there. So my moment is 30 kip feet. I convert it to inches. The Y sub T that I'm looking for is halfway minus the 2.5. So 15 minus 2.5 over 18,000 inches to the fourth times my modular ratio 6.57. And that equals 1.643 KSI in tension. And if I can go, let me go back. Yes, please.
I just wanted to ask about the second Y.
The second Y?
Yeah, how did you calculate that?
It's Y is from the neutral axis
Right.
to whatever it is you're trying to find a stress at.
Right.
So the distance from the neutral axis to the bottom of the beam was 15 inches.
Right.
The distance from the neutral axis to the center of the steel is
Okay.
15 inches minus 2.5 inches.
And that's because the steel was located 2.5 inches from the bottom.
Yes.
Okay.
Okay. So the equation my over I is based on the moment of inertia of the whole concrete beam. So my over I gives you the stress in the concrete, but I wanted a stress in the steel. So you have to multiply by N, the modular ratio, to get from the stress in the concrete to the stress in the steel. So let me jump back ahead to where we were. So the stress in the concrete, there is no modular ratio there, but the stress at the steel, I have to put in the modular ratio. And consequently, the stress in the steel is going to be much higher than the stress in the concrete. Even if they're at the same level, the stress in the steel is much higher than the stress in the concrete because the strain is the same. At the same elevation or the same level, the strain in the concrete and the strain in the steel are always the same. So for the same strain, the stress in the steel is going to be much higher than the stress in the concrete. Does that make sense to everybody?
Yeah.
Okay, good. Okay, part B, we want to find the cracking moment. So for the cracking moment, first of all, we need to find the modulus of rupture. Lambda is equal to 1 for regular weight concrete. So the modulus of rupture is minus 7.5 lambda square root f prime c. 7.5, 1 square root 6,000 is minus 581 psi, basically. And this is correct. It is negative because it is concrete in tension. So M cracked is minus the modulus of rupture, I gross over Y. So you have, you barely see it, but there's a negative times a negative 18,000. I don't know why I carried that inch to the third problem. I definitely got to fix that. Bear with me a second. I'm going to write this down. Lecture 2, fix I gross inch to the third. Okay. And we get 697.2 kip inch. Again, another note on this, I'm going to try to be better at this, but the units in this equation are kips over inches squared times inches to the fourth divided by inches. So your answer is kip inch. If you divide by 12, you get to kip feet, 58.1 kip feet. Most of the design answers and the factored loads, most of the time in reinforced concrete, kip feet is a more appropriate measure. But most of the equations that we have spit out kip inches. So please be aware of your units between kip inches and kip feet. Okay, concrete in tension is negative. Steel in tension is positive. So these are the correct answers here. Any questions on example 1?
A question on part B for
Yes.
the gross moment of inertia.
Uh-huh.
It's negative because it's in tension.
Well, the gross moment of inertia is never negative. Moments of inertia are always positive.
Okay, because the MCR equation,
Yes.
the last one.
Uh-huh.
So you said it was negative, right? The 18,000.
No.
Yeah.
And I'm glad you asked. The 18,000 is positive.
Oh, okay.
You see right there, the moment of inertia is always positive.
Okay.
Y sub t is positive. It's a measurement from the center to the bottom. But what's
Oh,
negative,
I see it now. Yeah.
the modulus of rupture is negative.
Yeah. It was a little. It's a tiny negative sign, right? At the beginning.
Right there.
Yeah. Okay.
Yeah.
I see it now. All right. Thank you.
Okay. Yeah, no problem. Let me do my little spotlighty thingy. Yeah, so there's a negative and there's another negative, so you get a positive. Okay, example 2. We're going to find the stress at the bottom of the beam and at the steel for a 60 kip foot moment. And part B, let's find the cracking moment for the following beam section. So now we have a T-beam. So this is a little different. The dimensions are as given, and F prime C for this T-beam is going to be 4,000 PSI. So for the solution, part A, I need to find the center of gravity of this T section. And for the rectangular section, it was obvious, but for the T section, I actually have to calc it out. So if you, quick review from mechanics, you remember that the center of gravity is the area of each part times the distance to the neutral or center of gravity for each part divided by the area. And you sum all the pieces from one to end. So this one's going to have 2 pieces, obviously. So you have the area of the top piece, 6 times 48 times 27 is the distance from the bottom to the center of this top flange, plus 24 times 9 times the distance to the center of this rectangle is 12, divided by the total area. And that gives you 20.57 inches, which is measured from the bottom to the center of gravity of the T section. Remember the parallel axis theorem? Anybody and everybody remember the parallel axis theorem?
Very vaguely.
Sort of.
Okay. Well, the parallel axis theorem says that for rectangular pieces, each piece about its own center of gravity is bh cubed over 12, the equation for moment of inertia of a rectangle. But if the center of the rectangle does not coincide with the center of gravity of the whole section, then you need to transform that area to the center for the whole section. So what you do is for each piece, you find bh cubed over 12 for that piece, plus the area of that piece times the distance from the center of the piece to the center of gravity of the whole section squared. So that's going to look like this. For the top piece, you have 48 wide, 6 high to the third time over 12, and then the area is 48 times 6. The center of gravity of the top piece was 27 minus 20.57 squared. So that's the top piece. The bottom piece is 9 times 24 to the third over 12. 9 times 24 center of gravity is 12 minus 20.57 squared. Which
So
gives
how
you
did we find the 20.57?
right here,
Oh, right. Okay. Yeah, I'm sorry.
right there.
Yeah.
That's the center of gravity that we just found for the whole T section. Okay, so D is the distance from the center of gravity of that individual piece to the center of gravity of the whole section squared. And that gives us 39,003 inches to the fourth. Okay, now that we have the distance to the center of gravity and the moment of inertia, we can find the stress at the bottom of the beam. F sub C is my over I. So I plug in my minus, that's minus. I got 60 kip feet, 12 inches per foot. And the distance from the center of gravity to the bottom fiber, which is where my tension's going to be, is 20.57 over 39,003 inches to the third is minus 380 psi or 0.38 ksi. Other than inches to the third, everybody okay with this?
Yeah.
Okay. Stress at the steel. We're going to find my modular ratio again. So I got to find my modulus of elasticity. 57,000 square root 4,000 is 3,605 KSI. Steel is always 29,000. So my modular ratio is 29,000 over 3,605, which is equal to 8.04. So then F sub S is my over I times the modular ratio N, 60, 12 inches per foot, 20.57 minus the 2.5 inches to the center of the steel times 8.04 divided by 39,003. And we get 2.682 KSI. Any questions on part A? Okay. Oh, is the height of the bottom rectangle plus the center of the height? Oh, yes, yes. Okay, part B, find the cracking moment. Again, we're assuming this is regular weight concrete. So modulus of rupture, 7.5 lambda square root F prime C. Minus 7.5 times 1 square root 4,000. And we talked about this before, but even though this is 4,000 PSI, the PSI goes outside of the square root, or otherwise your units will really get messy. And this is equal to minus 474.3 PSI. How did you get 57,000? This equation here is given. It's in ACI code. Oops, sorry, just saw that was private. Okay, anyway, is that okay if somebody asks me a private question, I'll just answer the question without saying who asked it? Is that okay?
Yes.
Yes, okay, all right.
Yeah.
All right, very good. So please ask me questions any way that you feel comfortable. Go ahead and ask the question.
Professor, would you please explain F sub S, please?
Okay.
Or the YT portion of it?
Okay. Let me get to that in just a second. The question that was asked was, where did this 57,000 come from? And this is an equation given by the code. In the last lecture, I think I gave the code reference as to where you can find this, but this is in the code as a canned equation, if you will. And this is 57,000. There's no units attached to it because the PSI is attached to the F prime C. So this is given to you by the code. And now F sub S, the equation for stress anywhere on a beam is my over I. The y is the distance from the center of gravity of the beam to whatever it is you're looking for. So we're looking for the stress in the steel. So we need the distance from the center of gravity to the steel. Well, the distance from the bottom to the center of gravity is 20.57, and the steel is 2.5 inches up from the bottom of the beam. So that's y sub t is 20.57 minus 2.5.
Okay, makes sense. I didn't know it was 2.5 from the bottom.
You
But
know
it's
what?
still,
I
yeah.
think I missed that dimension. Sorry about that. I think you're right. I missed that dimension, but I'm assuming that the steel is 2.5 up from the bottom.
Professor,
Yes.
in the case that there's 2 rows of steel beams, where would that distance be exactly?
That's a great question. It's at the center of gravity of the steel. So if you had 2 rows of 2 bars, it would be right in the middle between the 2. But if you have unequal rows, like you have 5 and 2, you have to basically use this equation right here and solve for where the center of gravity of your steel is.
Sounds like fun. Thank you.
And we'll get to it. I'll show you an example later on that does exactly that. Okay, so the cracking moment is negative of the modulus of rupture, moment of inertia over y. I plug in my values that I just found here, and I put this in KSI, so minus 4.474 KSI, 39,003 inches to the fourth over 20.57 inches gives you 898.8 kip inch or 74.9 kip feet. And that's the answer to part B. So to say it in another way, let's say it in the reverse. If this was the beam I had, and I applied a moment to it of 74.9 kip feet, that would be just enough moment to create the very first crack at the bottom of the beam. Concrete in tension is negative. Steel in tension is positive. And that's it for that example. Any questions on example 2? Okay. Once a concrete beam cracks, then the section has to rebalance itself between the concrete in compression and the steel in tension. Any concrete in tension is ignored for an analysis. A new neutral axis will be found whereby the first moment of the concrete above the neutral axis is balanced by the first moment of the transformed area of steel below. First moment is another way of just saying the area of times the distance to the neutral axis. You'll see that in a second. Okay, so if I had this beam, this is the shape of the beam, and this is the moment of inertia based on this shape before it cracks. But after it cracks, it looks more like this. It rebalances itself. And the beam's not going to crack just a little bit. Once the beam cracks, it keeps on cracking until it comes to a new balance point. And so we can solve where that balance point is. This is before cracking. This is after cracking. So again, after the beam cracks, any concrete down here that was in tension is ignored. So this is how we're going to analyze it. We're going to say that the neutral axis is oriented immediately at the bottom of this area of compression. So all the concrete above the neutral axis is in compression, and all the concrete below the neutral axis has disappeared. The steel here has to be transformed into an equivalent area of concrete. You can't find the moment of inertia of different materials. It doesn't make any sense because different materials have a different modulus of elasticity. You have to transform all of your different materials into one solitary material that has the same moment of inertia. Since most of the concrete beam is made out of concrete, then it makes the most sense to transform the steel into an equivalent area of concrete. And then what we're going to do is take the first moment. So as I said, the first moment is this area of concrete times the distance from the center to the neutral axis. And that's got to be equal to this area of steel, which is transformed into an area of concrete, times the centroidal distance to the neutral axis. Those two have to balance each other. So we're going to solve this by defining the depth of the concrete as x and the depth of the steel as d minus x. And I don't think we talked about this yet, but d is the standard concrete symbol for the depth of steel from the top of concrete. Okay, so here's my symbols. From the top of the concrete beam to this new neutral axis is labeled x. From the top of concrete to the center of the steel is D, and that's going to be a common theme. We're always going to be calling this D, from the top of the beam to the center of the steel. The area of the concrete is B times X. The area of the steel is this N modular ratio times the area of steel. Okay, is everybody on board so far?
Yes.
Okay. So the first moment of concrete is the area times y. And so that's going to be equal to B times X is the area. Y is X over 2 to the neutral axis. So half of X, it's the center of a square, rectangle, is X over 2. So Bx times X over 2 is Bx squared over 2. That's the first moment of the concrete half. First moment of the steel is the area of the transformed steel. The little t means transformed. So the transformed steel times y, which is going to be the modular ratio N times the area of steel times a distance of d minus x gives you this distance right here. You have to equate the two to equal each other, because again, they're balancing each other, and solve for x. X will represent the distance to the neutral axis. Finding the moment of inertia of the resulting section yields the cracked moment of inertia, I cracked. Okay, so if that makes sense, let's do an example where we find the cracked moment of inertia, and then we find the induced stress from a 75 kip-foot moment at the concrete, at the top of the beam, and at the steel. For this example, we're going to use 6,000 PSI concrete, and we're going to use 4 number 8s as our main reinforcement here. So for our solution, part A, first thing we need to do is how much steel do we have down here? Okay, so I'm not going to do this every time, but for the first couple times, until everybody has this memorized, if you turn to page 593 in your textbook, there's a table A.2. Under that table, if you look up a bar size for number 8, the cross-sectional area of one number 8 is 0.79 inches squared. So that's where that came from. You can also go to your code. Not sure that would be more convenient or less, but you can always go to your code. And that is on page 507. It is Appendix A. And there's an ASTM standard reinforcing bars for number 8. The nominal area is 0.79 inches squared. Okay, so that's where that comes from. I have 4 of them by definition of the problem. So 4 times 0.79 is 3.16 inches squared. My transformed area of steel now is I have to multiply it times the modular ratio times the area of steel. The modular ratio, 6.57, we just did that in the last example, so I just carried it through for 6,000 PSI concrete. You know what, though? As long as I'm thinking about that, I wonder if, bear with me a second. It does not. I was wondering if they had it in table 8.7 in your appendix, but they don't. So you'll have to calculate it. Okay, so the modular ratio came from the last example. 3.16 is my area of steel. This is my transformed area of steel. I have to equate the first moments. So here's my problem. I got 27.5 inches from the top of the beam to the steel, and my beam is 18 inches wide. So bx squared over 2 is 18 inches x squared over 2. And that is equal to the transformed area of steel times d minus x, which is 20.67 times 27.5 minus x. And so I have a quadratic now, don't I? I have 18x squared over 2 is equal to 20.76 times 27.5 minus x. So if I factor it and break it down, I have this. Solving the quadratic, I get
Professor, isn't it 27.5 minus x squared? Or am I wrong?
I think you're wrong. The only x squared is because 18 times x over 2 is right here. Bx squared over 2. 18x squared over 2. This area down here is 20.76 times a distance of 27.5 minus x. So this is just 20.76 times minus x.
Oh, okay, never mind. I was confused. Thank you. I got
See
it.
it? Okay.
Okay.
All right, good. So this is how you set the problem up. I mean, once you've done this a few times, they kind of fall in line about the same way. And however you choose to solve a quadratic is up to you. Most calculators have some sort of a quadratic solver. You could always do the, oh gosh, I don't even remember it now. What was it? B squared minus square root AB something something over something. You could do that too if you wanted to torture yourself. But however you choose to solve it, get to an answer. 6.89 is the real root of this equation. And now we're going to find where the neutral axis is. So we're going to find the neutral axis by summing these pieces from the bottom of the beam. So I have 18 wide times 6.89 high, we just solved for x, times 30 minus half of this, 6.89 over 2. That's the concrete part. Plus 20.76 times 2.5 is 2.5 up from the bottom, divided by the total. And that gives me 23.11 inches. Now, here's where you can check your work. If you did this correctly, if you balanced the first moments correctly, then x should be the distance to the neutral axis. That's the definition. So you can check your work by also saying that the distance to the neutral axis should be 30 inches total minus x, which is 6.89. And that gives you 23.11, which equals 23.11. And so we're okay. Any questions so far?
So when we're trying to solve for x, I understand that it's a quadratic, meaning that there's going to be two x's. You just choose the positive one, or?
Yes.
Okay.
Yes. In fact, I'll do it right now. I'm pretty sure it's always like that. But if I go 9, and then I carry that over, that's 20.76. And then I got minus 570.9. Okay, so for this example, I had 6.89, and minus 9.20. So it's super simple to figure out which one to use. It's always the positive root. Okay, now that we know the properties of our section, we know how much area of transformed area steel, we know how much concrete we have, and we know how far up from the bottom each one of these two pieces are, we can now solve for the moment of inertia. So the moment of inertia for the concrete is just the moment of inertia of this rectangle, bx cubed over 12, plus b times x times the distance from the neutral axis squared, which in this case would just be x over 2. So that's the concrete, these two terms. Now for the steel, here's a little simplification for the steel. We consider that the steel is 1 inch high and 20.76 inches wide, just for visual, just so that we can visualize what this is doing. But we don't actually take the moment of inertia of steel about itself, because it's pretty negligible. If we did, it would be 20.76 times 1 to the third divided by 12. So that's less than 2 inches to the fourth. It's negligible. So what I'm saying is, for this steel rectangle, you can ignore the moment of inertia about its own centroid and just focus on the area times the distance squared. The area is the transform area of the steel, 20.76, times a distance of 27.5 minus 6.89 is that distance there, squared. And what we get is 10,781 inches to the fourth. How much did we have before? We had 18 times 30 to the third divided by 12. So before we had 40,500 for the gross moment of inertia, and we only have 10,780 for the cracked moment of inertia. Let's see, there was a question. Distance to the centroid can't be negative. No. And if it is, as to the person asking the question, it doesn't matter. If you put 6.89 minus 27.5, you'll get a negative, but then you're squaring it anyway, right? So in this term here, it doesn't ever matter which one you put in front of the other. It's the difference that matters because you're squaring it. Does that make sense? Okay. The big point, the bigger picture here is that a concrete beam loses, what, 60 to 70% of its stiffness once it cracks. And that's the bigger takeaway, is that once a concrete beam starts to crack, it loses a lot of its stiffness. And that's going to come into play in a few lectures when we talk about deflections. Part B. Part B, let's find the stress from a 75 kip-foot moment, both at the concrete at the top of the beam and at the level of the steel. So we use our F sub C, my over I. In this case, y is the distance from the neutral axis to the top of the beam. Well, that's x. So y is 6.89. Don't be fooled into trying to just think it's 15 again, because that's the center of the gross moment of inertia. We're not interested in the gross section anymore. We're only interested in the cracked section. So y is by definition 6.89. We have our 75 times 12 inches per foot, negative, and my cracked moment of inertia goes down here. And we have minus 575 PSI, tension at the top of the beam. That's a typo. I was looking for at the top of the beam. And where did I? That's not supposed to be a negative right there. Okay. Sorry, guys. I gotta fix another typo. The top of the beam is in compression. So concrete in compression, that should be positive. So this is slide 129, fix F sub C. Okay. Okay, stress in the steel, my over I times N, we still have to use the modular ratio. So I have 75, 12 inches per foot. Now the distance to the steel is my distance to the center of gravity, 23.11, minus 2.5 to get to the level of the steel, over my cracked moment of inertia, times my modular ratio. And that gives me 11.3 KSI. So that jumped up quite a bit, didn't it? In the previous example, we had like 2 KSI. Now we have 11 KSI. So once the beam cracks, all that tension that was in the concrete gets transferred to the steel. That's why we put the steel there, really. But this is a good indicator of what the behavior is doing once the beam cracks. Any questions about example 3?
So Professor, what we basically do is just find X and then solve everything based on X, just like the other problems.
That's correct.
Okay.
Yep. The only thing that changes is your section doesn't look like this anymore. Now
Right.
your section looks like this. And yes, you got to solve for X so that you can get your hands around what this section really is.
Right. And then another thing is we don't consider the moment of inertia for the steel part.
Yes. Well, sort of. You
Okay.
do consider the steel in calculating the moment of inertia, but you do not consider the moment of inertia about itself. That's what we're neglecting. See, this term is a big term. That's a big number right there. But the moment of inertia about itself is insignificant, so we ignore that. Does that answer your question? Okay, let's do one more example and then we'll take a break. So example number 4, now we're back to the T-beam. Same dimensions as before, steel's at 2.5 inches. We want to find the crack moment of inertia, and we want to find the stress from a 100 kip-foot moment at the concrete at the top of the beam and at the steel towards the bottom of the beam. This time, concrete is 4,000 PSI, and our steel, we have 2 number 7s. So our solution is going to follow the same method. Part A, I need the area of the real steel is 2 times 0.6. This comes from the text where I showed you. So I have 1.2 inches squared of steel. My transformed area of steel is the modular ratio, which we got from example 2 now, times the area of steel gives me 9.65 inches squared transformed. I have to equate the first moments. And so now here's what my beam's going to look like. Only a portion of the flange is going to be effective. The rest of the flange and all of the web is going to be in tension, so it disappears. And so I have X is measured through the compression block, and my distance from the top of the beam to the center of the steel is 27.5 inches. So again, Bx squared over 2 is 48 inches X squared over 2, which is equal to the transformed area of steel times D minus X, 9.65 times 27.5 minus X. We form our quadratic. We solve the quadratic, and I only have 3.13 inches. We can do a quick check that 3.13 inches is less than 6 inches. So my assumption that it was all in the flange is correct. Gets a little more complicated if it drops down into the web. I find my center of gravity like I did before. I take this area of concrete times the distance to the neutral axis. which is 30 minus 3.13 inches over 2, the area of the steel times its distance from the bottom, divided by the total area, I get 26.87 inches from the bottom of the beam to the neutral axis. I checked that. It should be the total depth of the beam minus x. So 30 minus 3.13 is 26.87. These are the same. I did my math correctly. Find my moment of inertia, cracked moment of inertia. I find the concrete about itself, BH cubed over 12. I find the concrete about the neutral axis, which is the area times the distance, 3.13 over 2 squared, and the transformed area of steel times its distance to the neutral axis, 9.65 times 27.5 minus 3.13 squared. I neglect the steel moment of inertia about itself. This all comes to be 6,222 inches to the fourth. And notice though, when we did the gross moment of inertia, we ignored the steel. When we did the gross moment of inertia, we were just looking at the concrete shape. But once it cracks, how much steel you have determines how balanced it gets. If I put more steel in there, then it gets balanced right here. And I need more concrete to balance more steel. So it absolutely matters how much steel you have in here to see where this balance point is. For part B, the stress is my over I, and I think I made the same typo. Minus 100, 3.13 is minus 604. The number's right, that's supposed to be positive. That's concrete and compression. So that is slide 158. For the steel, same thing, 100 kip foot moment, change it to inches, kip inches, and then distance to the steel is my neutral axis minus 2.5 times the modular ratio over the crack moment of inertia. And I get in my steel 37,789 KSI. Pretty high. Okay. Any questions so far on cracked moment of inertia? Okay. Let's say, everybody, let's meet back here at 6:10. What do you think?
Yes.
All right. I'll
Yes,
tune
please.
out.
Professor, can you leave it at the previous slide?
Sure.
Yeah, thank you.
There you go. Okay. I will be back at 6:10. Okay, I'm gonna get started. So if we don't finish all the slides for this presentation, in my mind, that's okay. I mean, I kind of put together a lot of material, and some of these presentations have more material than others, but I would rather that we just go at a pace where people are getting it and understanding it or have a chance to ask questions as we're going through this, rather than trying to just burn through it just to get to the end of each presentation. So far, I've created 2 makeup days, one before the midterm and one before the final. And I've got plenty of material for this class. So I'm not worried about not covering what we're supposed to cover. We got plenty of material for that. So we'll see how far we get tonight. We have until 7:05, if I remember right, is this class. So we'll just kind of see where we land, but please do not hesitate to ask questions or ask questions verbally or through the chat or what have you. If there's something that you're not getting, much rather stop and talk about that now than to have a misconception continue on through. So does that make sense to everybody?
Yes.
Very good. Okay. So our next topic is what's known as doubly reinforced beams. Doubly reinforced beams are beams that have steel detailed in the tension side, but also have some steel on the compression side. So some concrete beams will have steel detailed at both the top and the bottom of the beam. The steel at the top of the beam will be in compression when the beam resists positive moments, and so is sometimes called compression steel. When steel is in compression, it takes on some of the compressive forces that otherwise would be resisted by the concrete. In lecture 1, we talked about creep, increased strain under constant compressive stress. When steel exists in concrete experiencing creep, that steel will serve to arrest the creep and minimize the strain growth. Therefore, for calculating the cracked moment of inertia, I cracked, we consider the area of the compression steel to be 2N instead of just N to account for the added stress transferred to the steel from the concrete creep strain. In other words, the concrete at the top of a beam in positive bending will take on an immediate strain and the corresponding stress due to the load. But because of creep, that strain is going to increase over time. Well, if there's steel in there, the steel's not going to have it. The steel's not going to just allow an increase in strain without putting up a fight. So that steel will pick up more stress in the future as the concrete tries to strain under creep. So instead of just using N, the modular ratio, we're going to use 2N. In addition, compression steel actually displaces concrete in the compression zone. So wherever the steel is in the compression zone, there's no concrete there. And so the area of concrete must be removed when adding the area of steel. This is accomplished by subtracting 1 from the modular ratio. Therefore, all of that is to say, the transformed area of compression steel is taken as 2N minus 1 times the area of steel. In this class, generally speaking, whenever we're talking about compression steel, which I know I just introduced, but whenever we talk about compression steel, we put a prime. A prime S, A prime ST tells you that we're talking about compression steel. And there it is. Traditionally, compression steel is noted with an apostrophe. So A prime S is the area of compression steel. D prime is the distance to the compression steel from the top of the beam. Okay, so example number 5. We're going to basically redo example number 1, but now I've got some steel in the top of the beam. I want to find the crack moment of inertia, and I want to find the stress from 100 kip-foot moment at the concrete at the top of the beam and at the level of the steel. Concrete is 5,000 PSI this time. The top steel is 2 number 7s. The bottom steel 4 number 9s.
Professor,
Yes,
can you go back to the previous slide?
sure. There.
Yeah, this equation that you have, where did the 2n come from again?
It came from this description right here.
And what's the a prime st? Because you have a prime s. What's a prime st?
Transformed.
Oh, okay, okay. Thank you.
Yeah,
Sorry.
no. Don't apologize. These are great questions. Please always feel free to ask your questions whenever they come up. You don't worry about interrupting me. And remember, whenever you have a question, there's probably 30 other people who have the same question. So I love it. I love questions. A prime st is the transformed version of A prime s times 2 times the modular ratio minus 1 due to what we just talked about with creep and the displaced concrete.
And Professor, I have a question for example number 4. Was the FC supposed to be positive as well? Because it's at the
Yes,
top.
it was. Yes.
Okay. Yeah.
Yeah, I carried over the same mistake apparently through each one of these.
Yeah, I was wondering. Thank you.
And I'll point it out. I'm guessing it's going to be on this one too, so I'll point it out. Okay, so part A, we have 5,000 PSI concrete now, so I can't use the modular ratio from example 1 or 2. We have to recalculate it. So I need Young's modulus for modulus of elasticity. 57,000 square root of f prime c gives me 4,131 KSI. Steel is always 29,000. Modular ratio is 29 over 4,031, 7.19. Area of steel at the bottom is 4 times 1, and 1 is the area of a number 9. Get this from the back of your text. It's 4 square inches. Transformed area is a modular ratio times the area of steel, 7.19 times 4, 28.76. This is the flexural steel, or the tension side steel.
Professor,
Yes.
can you explain again why you used the modular ratio in this part of the problem?
Because I need to transform the steel into an equivalent area of concrete so that I can find where the center of gravity is and the moment of inertia. And I'm starting with the tension steel. The tension steel has a modular ratio of n, but it's the compression steel that's going to have a modular ratio of 2n minus 1.
Thank you.
Did I hit your question, or was it something else?
Yeah, you answered it. Thank you.
Oh, okay.
So, Professor, is it always the steel at the top of the beam that's in compression, and then the one in the bottom is in tension?
Almost always. For this class, because it is not my intention to massively confuse everybody, especially on day 2, for this purposes of this class, assume all these beams that we're doing are simply supported. A simply supported beam has positive moment, so the top of the beam is in compression, the bottom of the beam is in tension. There are cases, very real examples, where it's the opposite, where you have negative moments. If you have negative moments, then the top of the beam is in tension, the bottom of the beam is in compression, and everything is backwards. Everything's reversed. I did not want to massively confuse everybody, so all of these examples are positive bending. So the compression's at the top, tension's at the bottom, and any steel at the top is compression steel.
Okay, thank you.
Okay, so A prime S, now the prime tells you that this is your compression steel. 2 times the area of a number 7 bar is 1.2 inches squared. And the transformed, here's where the 2n minus 1 comes in, because now this is compression. And 2 times 7.19 minus 1 times 1.2 gives you 16.06 inches squared. We have to equate the first moments. But now we have two pieces on the compression side, one piece on the tension side. I have the area of concrete, which is B times X, but I also have this transformed area of steel, which is equal to the 16.06 inches squared. And on the tension side, I have the transformed area of steel, 28.76 inches squared. So on the compression side, I have bx squared over 2, but I also have a prime st x minus d prime. So the distance to the neutral axis is x minus d prime. This equals 18x squared over 2 plus 16.06 times x minus 2.5, which all equals the tension side, the transform area of steel on the tension side times d minus
Professor?
x. Yes.
I have no idea where that equation came from.
Professor.
Okay.
Professor, is the plus a prime st because the steel also acts as compressant? That's why we don't minus it?
Yes.
Okay. Thank you.
Okay, but I'm more concerned about the first question, which basically said I completely lost.
Yeah, this where the equation came from.
This equation?
Yes, that one.
All right. Okay. This is the same equation we've done on the last last two examples. It is equating the first moments. The equation is taking each area times the distance to the neutral axis. Everything on the compression side is on one side of the equal sign. Everything on the tension side is on the other side of the equal sign. So what we did before, you only had 18x squared over 2. That's all you had on the compression side was equal to the area of steel times d minus x was on the tension side. All I've done is added the compression steel as another part. Everything in compression is on one side, everything in tension's on the other side. So I added the area of the compression steel, 1606, times its distance, x minus 2.5. Does that help?
Oh, okay. Yeah, that I follow. Thank you.
Okay, okay. So we're just adding up pieces. Everything on the compression side, everything on the tension side has to equal itself. So this is the compression side, this is the tension side, which is the tension steel times the distance to the neutral axis. Now, if I take all of these numbers and fine tune it down, I get this quadratic. Okay, so this quadratic is just 18 over 2 x squared, and I got this factor, and I got this factor, and I just whittled it all down to a quadratic equation. Solving the quadratic, I get x is equal to 7.44 inches. That's the distance from the top to the neutral axis. Okay, now if I did this correctly, then if I find the center of gravity, it should equal 7.44 inches down from the top of the beam. If it doesn't, then I had a mistake in here someplace. So this looks a little intimidating, but it's really the same thing. It's the area of concrete times the distance to the neutral axis. It's the area of the compression steel times the distance to the neutral axis. I'm sorry, I misspoke. This is the area of concrete times the distance to the bottom of the beam, 30 minus 7.44 over 2. So area of concrete times distance to the bottom of the beam, plus area of compression steel times the distance to the bottom of the beam, plus the area of the tension steel times the distance to the bottom of the beam, divided by the total area of all the parts. And this gives you 22.56 inches. If this is correct, then 30 minus 7.44 should equal 22.56 inches, and it does. So we have found the correct neutral axis for this section. Everybody still okay?
Yeah.
Okay. So the next step is I need to find the moment of inertia. So the moment of inertia is the moment of inertia of the concrete about itself plus its area times the distance to the neutral axis squared plus the area of the compression steel times the distance to the neutral axis squared plus the area of the tension steel times the distance to the neutral axis squared. Both steels, I've ignored the BH cubed over 12 term because it's negligible. Okay, so 2 terms for the concrete, 1 for the compression steel, 1 for the tension steel. And that all adds up to 14,436 inches to the fourth. Now that we have the center of gravity and the moment of inertia for the cracked section, now we can find the stress. And I'm sure I carried the same mistake over every one of these. So My over I is 100 kip feet, 12 inches per foot. 7.44 is the distance from the neutral axis to the top of the beam, divided by the crack moment of inertia, is 618 psi. Yes, this is supposed to be positive, and I'll fix these. So the top of the beam is experiencing 618 psi compression. The steel, and this is the tension steel, My over I times the modular ratio, 100 times 12 inches per foot, times the distance from the neutral axis to the center of the steel, times the modular ratio over the crack moment of inertia, gives us 11,989 KSI. And I also found the stress at the compression steel. So the compression steel is multiplied times 2N. So we have 100 kip feet times the distance from the neutral axis to the compression steel times 2 times the modular ratio over the crack moment of inertia. And that's only minus 5.905 KSI. This negative is correct. Steel in compression is negative. So that is correct. And the 2N again comes from the conversation about the creep in the concrete. Any questions on example 5? Yeah.
How about the concrete here, Professor? FC, should it be positive?
Yes, it should be positive. Yes.
Okay.
That should be positive.
Yeah, thank you.
Okay. Okay.
Professor.
Yes. Yes.
So let's say that in the real world, there's a doubly reinforced concrete beam.
Yes.
And let's say that it's the same case as in our example where there's tension on the bottom and compression on the top.
Uh-huh.
Would that top reinforcement be like, I don't know, pre-stressed or post-tension?
No, no, that's a whole different ball of wax. You're actually talking to the right guy. That's what I do for a living is pre-tensioned and post-tension stressing. But that top steel could be pre-stressed steel. The bottom steel could be pre-stressed steel. It's just a matter of choice, but it's beyond the scope of this class. So hopefully I'm not dodging your question. You can pre-stress any of this steel. You don't use rebar, you use strand, but you could substitute, you could take some of the rebar out, put pre-stress in, and analyze the beam. And there's a lot of advantages to that. But
it would like, I don't know, increase the strength, right?
Yes, and it also decreases your stresses if you put the pre-stress in the right place.
Got it, got it.
So, but without dodging the question, because that's pretty much what I do every day, but it is beyond the scope of this class. There's a whole other class dedicated just to pre-stress design.
Okay, thank you.
Okay. Any other questions? Okie doke. So now we're going to talk about ultimate strength level for a little bit. If we remember, ultimate strength level we assume the strains are quite advanced now. And the code defines the maximum usable strain as this number here, 0.003 inch per inch. At this level of strain in the concrete, again, the top of the beam is in compression, the bottom of the beam is in tension. At this level of strain, the steel has yielded and the concrete is in this plastic shape, okay? So there are 8 assumptions to strength design. And this is kind of like the intro. We got a few more lectures to go. So don't worry if this doesn't all make sense in the first go at it. But just as an intro to strength level, we have 8 assumptions to strength design. Number 1, the strain in the concrete is always equal to the strain in the steel. So if I use similar triangles and I figure out what the strain is right there, then the strain right there is in tension, but it's the same for the concrete as it is for the steel. If I had steel in the top, like compression steel, then the strain in the compression steel would be exactly equal to the strain in the concrete just around it. So that's assumption number 1. It's not always true. But for all intents and purposes, it's pretty darn close to true. It assumes that's why the reinforcing has those little nubbies on it. It assumes that the concrete and the steel bond and mechanically interlock with each other. So whatever the concrete's doing, the steel is doing the same thing, okay? That's assumption number 1. And it makes our lives beautiful because it means that we can solve with similar triangles. We can solve anything about the strain condition here, and we know what's going on with the steel. Number 2, strains are linear. And this is pretty darn close to being true, with the exception of really deep beams. Deep beams don't behave in a linear fashion, but also deep beams are outside the scope of this class, so you don't have to worry about it. For the purposes of this class, strains are linear. And all that means is on the strain diagram, this is always a straight line. We don't know what the slope of that line is. We don't know where the intersection of that line is, but we know it's a straight line. And that helps us immensely. Number 3, modulus elasticity for steel is always taken as 29,000 KSI. That's just a given. Number 4, plane sections remain plane. This is a little more difficult to explain. I think you guys got this concept in mechanics of materials, but it basically means that we're not looking at large deflection behavior, we're looking at small deflection behavior. The curvature of the beams when they're bending is small enough that we're not going to get any weird effects from a large curvature. That's basically what it means. And it also means that if you have a beam in bending, then you can take the moment diagram and find the strain and the stress from the moment diagram. Everything acts the way that you would expect it to act. That's basically what that means. Concrete in tension is ignored, just like we did for cracked moment of inertia. For ultimate strength level design, concrete in tension is ignored. So what that means is on the stress diagram right here, technically speaking, you have a little bit of concrete right here in tension before you get to the modulus of rupture on the strain. So in reality, there's a little blip right here of concrete in tension. Forget it. Who cares? Doesn't matter. Insignificant. So to simplify our lives, there is no concrete in tension. Concrete is only in compression. Number 6, concrete is inelastic at strains epsilon sub c above about 0.001 inch per inch. And that goes back to that strain diagram. that I was talking about that says that above this strain level, the concrete is acting in a plastic manner. Number 7, the section is considered failed at epsilon C above 003. That's 003, that's strain level. That's a code requirement. That's written right into the ACI code. And you got to draw the line somewhere. It doesn't really change the outcome if you change this number a little bit, like the European code uses 0035, doesn't change the answer significantly. But you do have to draw the line and base it on something. So this is going to be our assumption is that a concrete beam is at its ultimate strength level when the strain hits 003. That's it. And number 8, concrete compressive stress can be approximated with the Whitney stress block. We will elaborate on that a little bit, but what it means is we're going to replace this somewhat complicated stress pattern with a simplistic rectangle. That's what we're going to do. Okay, so to calculate the nominal strength of a concrete beam, assuming the steel will always yield prior to the concrete crushing as required by ACI code, then we know the tensile force is going to be the area steel times the yielding stress of the steel. We know this because we're always going to demand that the strain in the steel is enough to yield the steel when the concrete hits 003. The compressive force will be the integration of compressive stress from the top of the beam to the neutral axis and across the width of the beam. One approximation for the concrete stress as a function of strain is, and this seems a little complicated at first, but this is to say that F sub C, the stress in the concrete, is equal to 2 times F double prime C, the strain in the concrete over epsilon naught, over 1 plus the strain in the concrete over epsilon naught squared, where F double prime C is equal to 90% of F prime C, epsilon naught is equal to 1.71 F prime C over Young's modulus. And if I plot this, this is what it looks like from a strain of 0 to a strain of 003. So this is the entire usable strain for concrete. And this is what the stress looks like across the total usable strain. Okay? Any questions so far? Okay.
Listen.
Yes.
What does that equation represent next to the graph that you have?
This
This one?
equation here?
Yeah.
This equation is this equation. So in this equation, which is this equation, F double prime is a constant. This is something you can calculate. And epsilon naught is also a constant. So epsilon naught here and here, and F double prime C here are constants. So in this equation, the only variable is epsilon C, the strain in the concrete. So this is giving you stress FC for any given strain epsilon C. That's what this is telling you. So what this is showing you is when the strain in the concrete is 0, obviously you have 0 stress. When the strain in the concrete is 003, you have this stress level here, and it follows this curve.
Thank you.
Okay. So concrete compressive force is the summation of the compressive stress. And so what this is representing is this is an integral from 0 to C of the stress. This equation here is this equation here. So basically all we're doing is just integrating all of this stress across the width of the beam from the neutral axis, from the top of the beam to the neutral axis. That's what this is. Where C is the distance to the neutral axis, B is the width of the compression zone, epsilon U is the ultimate strain taken as 003. So I substituted in the strain, ultimate strain. And epsilon C is the concrete strain as a function of x dx. Okay, so what this is illustrating, so here's F prime C again. So you see this shape from 0 to 003 is really this shape from 0 to 003. You just turn it on its side. And so that equation that I just gave you here for C tells you the total force of all this stress. Stress times area is a force. The force C is equal to that expression. But where is that force being applied? What's this A prime number to the center of that force? Well, we can find where the area is or where the force is being applied by taking the same equation, but added x in there to find the first moment. And then A is equal to the force divided by, actually that's backwards, darn it. Now I have to fix that one. Slide 243. A prime is equal to Q over C, not C over Q. But this tells you where, so we know how much force and we know where the force is. Now that we have C, T we found is just the area of steel times the yield and their locations. We can now sum moments to find our capacity M sub N. Anytime you see this little n right there, that stands for nominal capacity. So M sub N is the nominal flexural capacity. M stands for moment. So M, N, the nominal capacity, if I sum my moments about C, then the moment capacity is T times the distance to C, which is D minus A prime. So I can sum my moments about any point, but it's really convenient to sum your moments about C, because then you only have one component, T, times this distance, where M sub N is the nominal flexural capacity of the beam. Okay, so I'm going to go through this last example. I think this is the last example fairly quickly. This is, I got to tell you up front, this is not how we're going to design regular concrete beams. This is not our normal design method. I'll give that to you next lecture. This is just to show you the mechanics of the concrete. I'm trying to explain what the concrete is really trying to do before we go to our next example, next lecture, and we simplify everything until it's really simple and boring. So, does that make sense to everybody?
Yeah.
How did you, what does it represent? Okay, we do have another question. I will try to explain this. Okay. They have done extensive experimental testing over the last 90 years. I mean, reinforced concrete has been around since the early 1900s or even before then. They have done tons of experimental testing. And what the experimental testing has done has established that when you load up concrete in compression, and it doesn't even have to be a beam, it could just be a chunk of concrete, and you just put it in compression, they will measure the stress and they will measure the strain in the compression machine. And when you load up concrete in compression, you get this curve. This is just a fundamental curve of the beauty and magic and mystery of the material concrete. This is just what it does. So they've come up with all kinds of different experimenters and investigators who write peer-reviewed structural journal articles, try to come up with expressions that model this behavior. None of these expressions are exactly right. None of them. And I could give you half a dozen other expressions that try to model this behavior as well. They all have kind of the same shape, but they all vary a little bit in the way that they formulate it. So I'm glad you asked this question, because this is, I might have just skipped over this. This is something really, really important to concrete. Concrete is mysterious. Concrete is a conglomeration of cement and water and sand and rock, and it just does whatever it wants to do. All that we can do as human beings is just try to predict it as best as we can. So we come up with these models. We have different models to predict different stuff. None of them are ever exactly right, but they're close. So hopefully I'm answering your question. This is a idealized model that creates this shape that gets kind of close to what the concrete would really do. That's all it is. The concrete really does what it wants to do, and we came up with this expression to kind of get close to modeling what it does. Okay, so we got down to here. Okay, so what we're going to do is we're going to use that model, that expression. And again, totally upfront and honest, we're not going to use this really complicated model to design concrete beams. Don't freak out and start dropping my class because I don't want to use integrals. We're not going to. This is just in the second lecture trying to express how complicated concrete really is and what is it that it's really trying to do before we get to next lecture and just simplify it so much that it just becomes boring and mundane. So that's next lecture. This is a complicated way to do it. If I have the same, this is our friend now, this is our beam, 30 inches by 18 inches, 6,000 PSI, 4 number 8s. What is the nominal flexural capacity of this beam? In other words, with this section properties and this strength and size of steel, theoretically, how much load should it take before this beam crushes the concrete and collapses onto the ground? How much load would that take? And the solution, first we need to find the area of steel. 4 times 0.79 is the area of 1 number 8, 3.16 inches squared. So the tensile force is 3.16 times 60. I don't even have to solve for this, do I? I know that steel is going to yield, so I can just use 60. And I get 189.6 kips is the force in the steel. Concrete properties. E sub c is 57,000 square root f prime c, which is 4,415 KSI. Epsilon naught, this equation is from the previous slide I just gave you. 1.71 times 6,000 or 4415 is about 0.0232 inch per inch. The physical representation, the meaning of epsilon naught is on that stress strain curve where it has this parabolic shape. This is the strain at which it peaks. This is the peak strain on that stress strain for concrete. F double prime C is 90% of F prime C. 90% of 6,000 is 5,400 PSI. And so here's my complicated integral where I can plug in all the values. all the constants, 5.4, 18, and I left x as a variable, dx. Now, I have to iterate little c until the tension equals the compression. The compression up here has to balance the tension down here. Sum your forces in the x has to equal 0, so tension has to equal compression. I don't know where the neutral axis is. I have to iterate it. So I iterate it because I put all this into a spreadsheet, and I just solved for 2.567 inches is the distance down that makes the concrete balance the steel. So if I plug 2.567 back into my integral, I can solve this integral, and it equals 189.6 kips. So that's good, right? The tension equals the compression. If they don't, there's a mistake somewhere because they have to. And if you're curious how I actually solve the integral, I have software. I have MathCAD. I think you can do it on MATLAB. I have MathCAD. Heck, there's calculators now. I think that will do it. But I chose the tool that I know, which is MathCAD, and I solved it using software. So please don't mistake me for some kind of math genius. I cheated too. So that's the total force in all the stress of the concrete. Now I need to know where is that force being applied. So I find the first moment, it's the same equation, but I add that little x right there, and I solve it again. And I get 195.1 kip inch. And the neutral axis is 195 kip inch over 189.6 kips, gives me 1.03 inches. This is the distance from the top of the beam to the center of all the compressive stress. So now my nominal moment capacity is 189.6 kips times a distance of 27.5 minus the distance to the center of the compression, 1.03, and I get 5,019 kip inch moment, or 418.2 kip feet. So again, to summarize, if I have 4 number 8s that are exactly yielding at 60 KSI and a beam that has exactly 6,000 PSI concrete, then theoretically, as I load this thing, I put load and load and more load and more load and more load, and it cracks and it deflects and it cracks some more, and then it really starts deflecting. When I get to this moment right there is when the top of the concrete will get to 003 on the strain, and this thing will crush. Once that concrete crushes, it literally collapses to the ground. It cannot hold any more load. It can't even hold its own self weight. So that's utter failure is when the top crushes. And that should happen at this moment for 18.2. Again, please don't be afraid of this class. When we get to next lecture, I'm going back through these slides. When we get to the next lecture, what we're going to do is we're going to substitute this equation and this formulation or model of concrete behavior with another model of concrete behavior that is far, far simpler. But I gave you all of this to give you an understanding of what the concrete is actually really trying to do in that concrete beam. Okay, we have a few minutes left. What kind of questions do I have?
Professor, is it okay if I ask a question like from example 4?
Sure.
Okay, you don't have to go back to it. I just want to know why we take the top portion of it. So in cracked concrete, so in example 3, I understand why we took the top portion of it. But in example 4, I just don't understand why we take the top portion of it and why we only take the one top part of it and we don't take that little T shape that's coming down.
Oh, on the T-beam.
Yes, yes.
Oh, okay. Well, I can go back to it. Okay, before I leave here, though, I had another question, and I can answer this pretty quick, I think. Okay, the question was, why do we iterate? And are you going to make me do that? Are you going to torture us by making us iterate? The answer is no. Well, I might, but not in the normal case. The reason why we have to iterate is this equation right here. I have two unknowns. I have x and I have c. I don't know how far c goes down such that 186 exactly equals 186. I don't know how far that distance is so that these two exactly and perfectly balance each other. So I have to iterate. So I plugged this all into software, and I just, took like 3 minutes, 2 minutes to just play around with numbers until I got this to equal that exactly. And then once I have it balanced, then I know that this is my correct distance to the neutral axis, and I get on with my life. What you will find is when we do the next lecture and we present a far simpler way to do all this, you will not have to iterate because we'll have an expression that does this in a much simpler way. Okay. Back to example 4, which I think was way up here someplace. It was the T-beam. Right there. That's your question, correct?
Yes.
Okay. All right. And if I go from this slide here. Okay. So the fundamental idea is that wherever the concrete has cracked, that concrete no longer exists. It's gone. So if this is the level where the crack goes up to, then all the concrete below the neutral axis is gone. That includes all of the web, and it includes some of the flange. But it's really no different than, let me go up to the previous one, this one. On the rectangular beam, I just went down until I got to the neutral axis X, and everything above the neutral axis is there working in compression. Everything below the neutral axis is gone, totally disappeared. Well, I did the same thing here. It's just, if the crack goes all the way up to here someplace, if the neutral axis is, say, right there, then everything above the neutral axis is working in compression. Everything below the neutral axis is assumed to be cracked and gone. So if that's the case, this beam doesn't know any different. It has no inkling that, let me try to draw this here. It has no inkling that it wasn't shaped like this in the first place. It doesn't make any difference. It doesn't care if this was originally this giant fat beam or this skinny T-beam. Doesn't make any difference because all the concrete below the neutral axis is gone.
Okay, now it makes sense. Thank you.
That makes
Appreciate
sense?
it. Yeah, it makes sense.
Okay. And we're going to talk about T-beams more. We're going to talk about doubly reinforced beams. That's a whole lecture, is doubly reinforced beams. And a whole lecture is T-beams on finding the strength, the nominal capacity of the beam. This was talking about it for crack moment of inertia for deflection purposes. Any other questions? Before I forget, actually, I think somebody already talked about this, but as long as I brought it up, on Blackboard is your first homework assignment. It's in a PDF form. Please download that and start working on that. That's due a week from today. And it basically just kind of goes over these topics of this lecture and the next lecture. And I think the first one's a little light. I think there's only 2 questions. They should be a bit more involved as we move along here. So that is basically my lecture today. Any last questions?
No. Thank you, Professor.
Okay, thank you, everybody. I did record this, so I will post it to YouTube probably tomorrow morning. And everybody enjoy your evening. I'll talk to you next time.
Have a
Thank
good
you,
day.
Professor. Have a
Thank you.
great day.
Thank you.